Swayam Prabha. Digital India. Educated India.
In this lecture, we will be discussing two topics. One is a system of reduced units, and the other one is long-range corrections. In MD simulations, we often use a set of reduced units, and it has several advantages. And we want to basically discuss what is the principle behind using reduced units and what are the advantages. So before we talk about reduced units, let us briefly discuss a principle called law of corresponding states. So for a simple system, fluid systems, if you plot the compressibility factor Z, which is defined as PV by RT, as a function of pressure for different temperatures, you would see certain behavior like this as a function of temperature. Okay, temperature increases in this direction. So this is for, let's say, species A. And then if I do the same thing for another species B, you will see another set of similar curves. Okay. So now if you try to normalize the pressure and temperature with respect to certain parameters, it turns out that all these curves can be collapsed into a set of universal functions. That is what's shown in this particular graph, where the compressibility factor is plotted against what is known as the reduced pressure, defined as pressure divided by the critical pressure of each of those components. And then these curves correspond to different temperatures, reduced temperatures defined as temperature divided by the critical temperatures. As you might know, for any pure substance, there is a unique critical point corresponding to a particular temperature and pressure, right? So this is the critical temperature, and then correspondingly you take a critical pressure as well. And then if you normalize the temperature and pressure with respect to the unique set of critical constants, namely the critical temperature and critical pressure, it seems that the compressibility factor for many chemicals fall on the same line. For example, if you take any one of these temperatures, for example, if you take Tr is equal to 1.00, so if you take each species compressibility data and then plot in terms of normalized pressure and normalized temperature, you see that they all fall in a set of family of curves. For example, if you consider Tr is equal to 1, for all the species like methylene, ethylene, ethane, propane, various set of alkanes, even nitrogen, carbon dioxide and water, certain species properties are taken, and you can see that they all nicely collapse onto the universal functional form. Therefore, we are able to show the compressibility factor can be defined as an universal function of reduced temperature and reduced pressure. Now, if you look at carefully in this set of data, the behavior of water seems to be little odd. You can see that it deviates, the water points correspond to the black circle, and you can see that it deviates from the general behavior in many places. Okay, and we know that because water has hydrogen bonding and it is polar, and it needs little more information than just a reduced temperature and reduced pressure. So if you want to account for many such compounds, we have to extend this universal function by including more parameters. One such example is what is known as the Spitzer correction by introducing eccentric factor, which takes care of the shape of the molecule. So, if you look at thermodynamics literature on equation of states, you will see many such generalized law of corresponding states and set of equations that can collapse the individual species properties into a set of general functions. So therefore, the law of corresponding state basically means that the equation of state is a universal function of reduced temperature and pressure. So we do this routinely in thermodynamics by developing equation of state in a reduced set of parameters. So what we have been able to do in classical thermodynamics for a macroscopic properties, we could also do something similar in the intermolecular potentials also. The law of corresponding state is not only limited for macroscopic systems, but also applicable at microscopic level. What I mean by microscopic level is at the atomistic and molecular level as well. To illustrate this point, what I have drawn on the left hand side is the Lennard-Jones potential for different systems. For example, the first curve corresponds to oxygen, the second one for chlorine, and the third one for benzene. All of them are Lennard-Jones potential, but they look different because for each of the species, the set of parameters epsilon and sigma are different. For example, for oxygen, epsilon value is somewhere here, whereas for chlorine, it is little higher in negative numbers. And similarly, if you look at sigma, for oxygen it is right here, whereas for chlorine it is right here. So, based on the set of parameters epsilon and sigma, we are able to plot a family of Lennard-Jones potential for these systems. Now, suppose if I renormalize or reduced the parameters here, for example, I can introduce a reduced interparticle distance as the interparticle distance divided by the respective sigma, and sigma depends on a particular species. Similarly, the pair potential V here can be normalized or reduced with respect to the energy parameter, which is epsilon. So, when I substitute these reduced parameters, you can see that this Lennard-Jones potential, which depends on two parameters epsilon and sigma, in the reduced space it becomes independent of those parameters. It becomes a unique function of, so V star becomes a unique function of just R star alone. So, all these curves, family of curves, can be now plotted into one single function in the reduced potential energy and the reduced interparticle distance. So, what we are able to do for equation of states, something similar can be done for intermolecular forces also by looking at an appropriate set of normalization constants or parameters. So, now what we can also do is we can extend a little further. Not only we normalize the potential parameters, but also we can define thermodynamic variables such as temperature and pressure and volume with respect to these molecular parameters. So, right now we are taking Lennard-Jones as an example case, but something similar can be done for other system of potentials also. So, in Lennard-Jones potential we have two sets of parameters epsilon and sigma. So, we can define that if temperature and pressure, if these are defined in terms of potential parameters, that is in terms of epsilon and sigma, then equilibrium and transport properties of the system can be written into certain universal function of reduced temperature and reduced pressure. So, this is the application of law of corresponding state for atomistic systems. So, in this limit, then we can actually think about redefining our temperature or reducing temperature with epsilon by kb. You might recall that epsilon by kb is in the units of temperature. Okay. So, therefore, we can define our reduced temperature as the actual temperature divided by epsilon by kb. Therefore, this too will have a non-dimensional unit. So, this basically comes as kBT by epsilon. So, this is one way of defining reduced temperature using potential parameters. And you may recollect that in the equation of state that I showed before, the temperature was reduced with respect to critical temperature. Sometimes we use with a star to illustrate its reduced unit, or you can also use a subscript R to say that it is a reduced unit. You can see that the choice of the parameters to reduce could be different. In this case, we are using epsilon by kb as a normalization factor for temperature, whereas here we are taking the critical temperature, which is experimentally available in many systems. Similarly, if you look at pressure, we had initially discussed that the pressure can be reduced with respect to the critical pressure, but in the molecular potential parameter space, you can define pressure as the reduced pressure as P times sigma cube by epsilon, and you can see that so P in here, P would be in Newton per meter square, and sigma cube would be in meter cube, and epsilon is in joules, that is Newton meter, and you can see that they all cancel, so that the P star becomes a non-dimensional number. Similarly, volume can also be normalized with respect to V by sigma cube, and then this V here is in meter cube and sigma cube is also in meter cube, so they cancel each other, so that V star here is a non-dimensional or reduced volume. Whereas in the equation of state, we would have used the reduced volume could be defined as volume divided by the critical volume Vc. Okay. So, these are two different ways in which temperature, pressure, volume could be normalized or reduced with respect to either macroscopic critical constants or molecular parameters such as sigma and epsilon for the case of Lennard-Jones potentials. So, if you extend this approach further, it appears that we can always choose a system of basis units for length, energy and mass as fundamental units or basis units, and then express all the other quantities in a set of derived units. For example, once you choose sigma, epsilon and m, and then we can define a time constant as a function of these three chosen units. For example, you may choose to define a non-dimensional or reduced time t star as t by tau, where tau is a time constant which is defined as square root of m times sigma square by epsilon. So, similarly, the energy can be written in terms of energy by epsilon, the total energy of the system, and the density can be written in terms of density times sigma cube, and force and surface tension, all this could be written in terms of sigma and epsilon. Not only the equilibrium properties, but even transport properties such as diffusivity, viscosity and thermal conductivity can also be defined in terms of the system of basis units. For any given property, if you want to find out what is the normalization or reduced system of units, all you need to do is you have to basically write, for example, let me show you this for diffusivity, how this expression was obtained, and then you can do this over for other quantities as well. For instance, we know that D is in the units of meter square by second. Okay, so we want to write D is equal to some D star times meter square by second, and for meter square, that is the length squared, we use sigma square. For time, we use tau, and tau is written as square root of m sigma square, like this. And then if you simplify this, you get so from here you can write a D star is equal to D times square root of m by epsilon sigma square. Okay, so by looking at the physical unit and then writing corresponding basis units for those dimensions, then you can show and you can derive the respective non-dimensional units. The same thing you can do for viscosity and thermal conductivity also. So, this system of reduced units is not only applicable just for Lennard-Jones potential, but you can also extend this for other kind of potential interactions. For example, if you are looking at Coulombic interactions between ionic species, then we know that the potential energy goes as 1 by r, where r is the distance between a set of charges, and where Zi, Zj are the number of charges in those ions. And then this epsilon 0 here, that is the permittivity of the free space given in terms of these units. So now what we can do is we can choose non-dimensional charges Z and non-dimensional energy and non-dimensional R as well. So in this particular problem, we define that Z star is given as Z divided by square root of 4 pi epsilon sigma times epsilon. So now if you take this expression, we write V as V star times epsilon. On the right hand side we write Z star I Please note that this is the Lennard-Jones parameter and this is the permittivity, they are not the same. Okay. So now you can see that these the product of these within the square root will cancel with this 4 pi epsilon 0. So what is left on the top on the numerator is Zi star Zj star times epsilon, and you have R star, and this sigma will get cancelled with this sigma. Okay, and then you have epsilon cancelling. So we have the reduced potential energy is simply given as reduced charge, product of reduced charges divided by simply R star. So you may note that even though in this problem we are talking about Coulombic interactions, in addition to Coulombic interaction there could be Lennard-Jones interaction also. That's why we are taking epsilon and sigma are as a system of basis units for energy and length, and along with that we are able to define a reduced charge, and with this definition of reduced charge then we get a reduced Coulombic potential of this form. And for any other given potential, square wave potential or Yukawa or other forms, you could actually define similar set of reduced units and then write them in a non-dimensional form. So what are the uses of reduced units? So we again invoke that from the law of corresponding states, the properties which could be equilibrium properties or transfer properties are basically the same at identical reduced states. So what do we mean by that? Let us consider two examples. Argon is considered at 80 Kelvin at 840 kg per meter cube. Okay, so this is one particular thermodynamic state for argon species, and then we take xenon at 112 Kelvin and at a density of 1617 kg per meter cube. So suppose if I plot these two species in temperature and density, you see that argon is here and xenon is here from their thermodynamic state point of view. Okay, so the xenon exists at this particular density and this particular temperature, whereas argon exists at this particular temperature and this particular density. However, if I normalize the temperature and the density using the expression T star is equal to kBT by epsilon and density rho star as rho times sigma cube. So the values of epsilon and sigma are different for argon and xenon. So if I take this 80 degrees Celsius here and then take the respective epsilon for argon and multiply with Kb, I will get this is to be 0.5. Similarly, I take this density and multiply with sigma of argon to the power cube, and then I find this to be also at 0.5. So the dimensional units of temperature and density for argon corresponding to 80 Kelvin and 840 kg per meter cube transform into a set of reduced units where reduced temperature and reduced densities are 0.5 and 0.5. Similarly, if I take the xenon's property of epsilon and sigma and then if I apply if I reduce the temperature and density, it turns out that for them also the reduced temperature and reduced densities are 0.5, 0.5. So in the reduced temperature and reduced density state space, you see that both argon and xenon are at the same conditions or same reduced states. So, even though in the dimensional unit the argon and xenon are two different thermodynamic state, in the reduced state they correspond to the same state. Okay. In such a case, then if I do a simulation at reduced temperature of 0.5 and reduced density of 0.5, then the same simulation results can be used for both xenon at this temperature and pressure, temperature and density, and for argon at this temperature and this density. Okay. So, that is how we are able to do very minimal set of equations in the reduced units and then use it for many system of species. So, that is what is basically mentioned here. A simulation carried out at T star of 0.5 and density of 0.5 can be used to measure properties of different species at different thermodynamic conditions. One single simulation applicable for many thermodynamic states for many species. So, that is one of the use of reduced units in MD simulations. Here is another example where experimentally calculated viscosities in reduced units is plotted as a function of inverse temperature. You may recollect, we have defined reduced viscosities using system of basis units by this expression. Okay. For a given species epsilon, once epsilon, mass and sigma are known, then we can reduce the viscosity into a non-dimensional form. Similarly, temperature is defined as kBT by epsilon. Again, this depends on each species. So, if you look at carefully here, it appears that the reduced viscosity plotted against inverse of reduced temperature shows a nice scaling behavior for certain species up to xenon, argon, krypton, carbon monoxide and nitrogen. So, they all fall nicely along a universal line. Whereas, if you look at oxygen, methane and this is methane, but with deuterated system, they show a pretty different behavior. Okay. They do not follow the kind of trend that we see here. So, it appears that for certain spherical non-polar systems, there is a universal scaling behavior of viscosity as a universal function of inverse temperature, whereas for other larger molecules and polar molecules, such a simple scaling is not enough. So, you may have to add a little bit more additional parameters, so that they can also be written in terms of certain universal functions. So, the point I am trying to make here is that both compressibility factor or equation of state and transport properties could be expressed as a universal function of reduced parameters for very many number of systems. So, you do not have to so once such a universal functions are available, then we do not have to do simulation for every single system. We can take simulation results from another system and then convert that into a corresponding reduced state, and that could be used for many other similar systems. And another advantage of using reduced units in MD simulation is that we are able to monitor whether there is any error coming up in the during the simulations. To illustrate this point, if you look at physical units that we involve in these simulations, so sigma is typically in the units of 10 power minus 10 meter in an angstrom units, and mass could be of the order of 10 power minus 23 grams, and delta t, the time step used in MD simulation, could be of the order of 10 power minus 15 seconds, and temperature pressure conditions are such that temperature can reach from 100 to 1000 Kelvin, pressure can range from 10 power 5 Pascal to 10 power 7 Pascals. So, you can see that we are looking at a very small numbers and very large numbers, and then we often do floating point operations in terms of multiplying or dividing with a large number and small number. So, and then in MD simulations we use finite difference method. So, all this will probably lead to certain overflow of numbers, because we might be looking at a very large number and very small number and anything in between. Whereas if you use a system of reduced units, then we know that all this reduced system of units will have a very short range of span, which will range from, let's say, 10 power minus 3 to 1000. That's a typical range of numbers for equilibrium properties as well as transport properties. So when you use reduced units in MD simulations, and you know that the range of parameters should be within a particular range between minus 10 power minus 3 to 10 power 3, and then during a simulation, if you see some very large number of the order of 10 power 20 or 25, which is very big, and you know that there is some issue in the simulations because you are not expecting such a large number in the reduced system of units. Whereas in physical units, we cannot distinguish between whether the error is coming up because of numerical instability or because of the properties themselves are in this order. So it's very easy to detect errors in simulations when we use a system of reduced units. Now we also have to now talk about, given a reduced units, how to convert back to a real units, and that is also very easy by looking at how we defined our system of reduced units. So once you know reduced temperature, you can find out what is the physical temperature corresponding to that particular reduced temperature by making use of the Boltzmann constant and the corresponding energy parameter epsilon for that system. Similarly, pressure can be converted from reduced unit to real units by multiplying with epsilon and dividing by sigma cube, and similarly for density also. So here is an example. Suppose if you want to compare simulation results done for T star 1 and P star 1 with the experimental data for, let's say, argon, and this corresponding reduced states for argon would mean the temperature of 119.8 Kelvin and a pressure of 41.9 megapascal. So the way we got this number is by plugging in the value of epsilon and sigma and mass in this set of equations, and then calculating what is the temperature and pressure for this particular set of reduced units. So we have looked at how to convert real units into reduced units, and also from reduced units to back to real units. So now we come to another concept of a long range correction or tail correction. So you might recollect that when we talked about periodic boundary conditions and calculation of forces, we talked about that we often define a particular spherical cutoff within which the intermolecular forces are calculated, and beyond that cutoff distance we do not account for any potential calculations. And the reason for doing that is that beyond a cutoff the potential energy is not very significant, and we don't want to waste computational time in searching for pairs which do not contribute to the potential energy. And this has this improves our computational speed, and we can actually analyze a larger system with a limited computing power. However, when we do this kind of a potential cutoff as a practical convenience, but then when we measure properties from simulations, these properties measured using a truncated potential will not be identical to a real physical system, and that can be illustrated here in this plot, where the solid line here is the phase coexistence between liquid and vapor for a Leonard-Jones system plotted as a function of temperature and density, and the critical point is here. But when you correct for this truncation by adding what is called the tail correction, the critical point actually is right here, and this is more realistic and more accurate than this one. So if you do a potential truncation and do not correct for it, we often underestimate the critical point in this particular case. So it's very important that after the simulation or during the simulations, we take care of how much we have ignored and how to correct for it. So that basically entails to adding long tail corrections or simply tail corrections. So the way we do this tail correction is by again going back to the use of RDF, the radial distribution functions, because we have shown that once we have the radial distribution function, we are able to basically calculate pair potentials or pair functions. For example, if you have any quantity A which is written as sum of pairs over sum of pairs, some pair functions are calculated, and then this can be expressed into in terms of an integral of the radial distribution function RDF, and we have shown for expression for energy and pressure accordingly. So now we are going to make use of these expressions and then add tail correction to the system. So let us take this energy first. So here we have this ideal part and then we have this non-ideal part. So now I am going to just split this integral. The integral actually goes from 0 to infinity, and now I am going to just split this integral from 0 to RC, which is RC is the spherical cutoff, and from RC2 to infinity. Now what we actually do in our simulation is we calculate these in our simulation because we take care of the potential energy up to a potential cutoff. What we have been ignoring is this part in the simulations, because we do not calculate potential from RC2 to infinity. So this is the part that comes from tail contribution or long range contribution, which has been ignored in the simulation. So now we want to take this expression and then try to see if we can analytically solve this and then add this correction at the end of the simulation or during the simulations. So now before we use this expression for tail correction, we make an assumption that the g of r becomes 1 for r greater than RC. So what I mean by that is, if I plot the g of r as a function of r, so this is a line corresponding to 1, so we are saying something like this. So beyond r is greater than RC, around this region the g of r is 1, and we take this as an assumption, which could be true because the potentials are truncating at r is equal to RC or below. So the particles or atoms do not interact with its neighbor, which is sitting r greater than RC. Okay, so then you expect that the distribution beyond r equal to RC is basically ideal like behavior. So the g of r becomes 1 there. Okay, so once I make g of r is equal to 1 in this integral, then my E tail becomes simply an expression which can be analytically soluble, because this is an integral over r square times the potential per potential times dr. And for potential like Lennard-Jones, we know that it is a function of 1 by r power 12 and 1 by r power 6, and this can be substituted here and then integrated in the limit of RC to infinity, and then you will see that the tail correction is proportional to the density of the system and the so this should be RC here. Okay, and these are also RC. So from here to here, what I have done is I have defined a non-dimensional tail energy by dividing this by epsilon. Okay, I take this epsilon here and then that becomes a non-dimensional energy. This rho times sigma cube becomes rho star, that is non-dimensional density, and then RC by sigma becomes RC star, etc. So for a given simulation at a given density, you basically calculate these quantities analytically, because we know RC, we know the density number and everything. So you calculate the total energy because of the neglected contributions and add it up to the total energy. So the total energy of the system then becomes the energy calculated in the simulations up to a cutoff distance RC, then another correction that we add, which we can calculate analytically from here. Now you can replace this potential with something else. If you do from other kind of a potential, you can always do this. There's only one catch here, that the V of r should actually decay as 1 by r power n, where n should be greater than 3. Otherwise you will see that this will not converge, this integration will not converge. It perfectly works for Lennard-Jones potential because it scales as 1 by r power 6 and 1 by r power 12. Whereas if you substitute for a Coulombic interaction which goes as 1 by r, you see that this E tail will not converge, but rather it will diverge. So this approach of tail correction then works only for short range interactions. When you have long range interactions such as dipolar or Coulombic interactions, we have to deal this separately in a different way. But this approach is valid only for short range interactions such as hydrophobic interactions or Lennard-Jones interaction, etc. And now we can also do something same for pressure correction. So, for the pressure, we have this ideal contribution and then we have this non-ideal contribution, which is written as a function of the GFR. So, here again we split this integral from 0 to RC and RC to infinity. You can see these expressions are exactly the same, only the integration limits are separated. And what we do in our simulations is we take care of up to RC, we take care of it, and this is the part that we ignore because we do not calculate virial from RC to infinity. So, therefore, we can use this expression, make an assumption that G of R is equal to 1 for R greater than RC. So, this number, this becomes just 1 and then we can substitute that here. So, the tail correction for pressure simply becomes the integral over from RC2 to infinity R square times the pair virial times dr, and the pair virial is defined as R times dV by dr, and then for Lennard-Jones potential you can take the derivative with respect to R and then multiply with R, then you get this, and this can be substituted here, multiply by R square, integrate it, substitute the limits, and then you get the correction for the pressure. This should be RC star. Okay. So, then this becomes the correction for the pressure. So, this becomes a kind of a constant quantity that can be added at the end of the simulations. Okay. So, this is the one that we calculate, pressure calculated in the simulation, and this is the pressure that we add as a long range correction. So, one important thing we have to remember is that when we do this correction for energy and pressure, it comes as a function of density, and the density is constant in NVT simulations or even NVE simulations. So, we can actually calculate these things post simulation and add it up as a correction. Whereas, when you do NPT simulations where volume is fluctuating, and because of that rho will also be fluctuating, so then we cannot add the correction at the end of the simulation in NPT simulation, but rather we should be doing on the fly. As the simulation goes on, at every time step we have to add the tail correction because the density itself is a fluctuating quantity and we will not be able to do it at the end of the simulations. Alright. So, to summarize, what we have seen in this lecture is that we are able to define a set of reduced parameters using molecular potential parameters such as epsilon and sigma for Lennard-Jones, and similar set of parameters for other potential as well. And we inspire from the law of corresponding states, which we use for describing the compressibility factor written as an universal function of reduced temperature and reduced pressure. And when you try to do this, when you try to use a system of reduced units, then all these equilibrium and transport properties can be written into a function of an universal function of reduced parameters. And the advantage of doing this is that maybe one set of simulations in reduced parameter space can be used for many systems in many real system of units. And it is also easy to spot errors when we use system of reduced units because we know there is a certain bound with which the reduced units are supposed to scale. And using the approximation that the G of R can be considered to be 1 beyond the spherical cutoff, we are able to analytically get a tail correction for pressure and energy, which are basically sum of pair functions. And we have demonstrated that for Lennard-Jones potential, but for any given potential which is short ranged, and you should be able to calculate the long range and long range corrections for energy and pressure.